Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Topic 8.2 Electrical Circuits. Welcome back. In our last lesson, we talked about basic electrical theory, voltage, current, resistance, and how energy behaves in a simple circuit. Now we're moving on to topic 8.2, electrical circuits. In this topic we'll look at the different types of circuits, series, parallel, and a combination of both, and we'll also talk about circuit symbols, measurement, and why most appliances are wired the way they are. Let's begin with topic A. Topic A, describing a series circuit. A series circuit is the simplest kind of circuit. All the components are connected one after another in a single path. Because there is only one path, the same current flows through every part of the circuit. Think of it like a single-lane road. If one car stops, all the cars behind must stop too. In the same way, if one lamp or one resistor fails in a series circuit, the entire circuit stops working. A good example is a string of old Christmas tree lights. One bulb blows and the whole string goes out. Series circuits are also used in control circuits where one device must operate before another can start, such as safety switches or emergency stop buttons in a motor control system. Topic B. Characteristics of a series circuit. Now let's look at the main characteristics of a series circuit. First, the current is the same through every component. Second, the voltage from the supply is shared between the components. Third, the total resistance is the sum of all the resistances in the circuit. And finally, if any part of the circuit opens, current stops everywhere. We can express the total resistance as R total equals A1 plus A2 plus A3. If three resistors, 20 ohms, 30 ohms, and 50 ohms, are connected in series, the total resistance is 100 ohms. If the supply voltage is 200 volts, the current equals 200 divided by 100, which is 2 amperes. That same current flows through each resistor. Topic C. Drawing and labeling a series circuit. Next, in topic C, let's imagine how to draw a simple series circuit. You'd show the voltage source at one end, a control switch, and then your loads or resistors connected one after another in a straight line. Every symbol would be labeled, the source, the switch, the loads, so anyone reading the diagram can easily follow the path of current from one side of the supply to the other. Even though we're saying this out loud, picture it clearly: a battery, a switch, and three lamps connected end to end. That's a series circuit. Topic D. Recognizing and using standard circuit symbols. Now in topic D, we'll talk about the correct standard symbols used in electrical diagrams. These are like a common language for electricians. A resistor is shown as a small zigzag line. A lamp is a small circle with a cross inside. A capacitor looks like two parallel lines. A switch is a simple break that can open or close. And a battery or cell is shown by a long line and a short line side by side. Knowing these symbols is essential because both exam questions and technical drawings use them all the time. When you can recognize these symbols quickly, you'll be able to read and interpret any circuit diagram confidently. Topic E. Describing a parallel circuit. Now let's move to topic E. A parallel circuit is one where components are connected across the same supply, giving each component its own separate path for current. That means each branch has the same voltage across it, but the current divides between the branches. An everyday example is a household lighting circuit. Each light fitting is connected in parallel. If one lamp blows, the others stay on because each has its own current path. This design is reliable and efficient, which is why almost all domestic and industrial wiring uses parallel circuits. Topic F. Characteristics of a parallel circuit. In topic F, let's talk about the main characteristics of a parallel circuit. First, the voltage across every branch is the same. Second, the current divides among the branches, depending on the resistance of each one. Third, the total current flowing from the supply equals the sum of the currents in each branch. And fourth, the total resistance is always less than the smallest branch resistance. The formula for this is spoken as 1 divided by a total equals 1 divided by a 1 plus 1 divided by a 2 plus 1 divided by a 3. For example, if you connect a 60 ohm and a 30 ohm resistor in parallel, 1 over a total equals 1 over 60 plus 1 over 30, which equals 1 over 20. So the total resistance is 20 ohms, smaller than either resistor on its own. Topic G. Drawing and labeling parallel and series parallel circuits. Let's move to topic G. When we draw a parallel circuit, we show several branches connected between two common lines, one for the phase and one for the neutral or negative side. Each branch has its own load and its own switch if required. A series parallel circuit combines both types. For example, you might have two lamps in series on one branch and another single lamp on a second branch. This kind of circuit is common in heating controls and other systems where we need different operating levels. When drawing these circuits, always label the supply, the loads, and the switches clearly so someone reading it knows exactly where current flows and how it can be controlled. Topic H. Correct connections for measuring instruments. Now let's talk about how to connect measuring instruments correctly. This is topic H. When you measure voltage, connect the voltmeter in parallel with the component, because it measures the potential difference across that component. When you measure current, connect the ammeter in series, so all the current flows through it. And when you measure resistance, isolate the supply and connect the ohmmeter directly across the component being tested. Always remember, voltmeter parallel, ammeter series, and ohmmeter isolated. A wrong connection, for example, putting an ammeter across the supply, could destroy the meter or cause an accident. Topic I. Why appliances are connected in parallel. Let's go to topic I. Most electrical appliances are connected in parallel, not in series, and there's a good reason for that. In a parallel connection, every appliance receives the full supply voltage, so each operates correctly and independently. If one appliance is turned off or fails, the others continue working. If we connected them in series, each one would only get part of the voltage. For example, if three 230-volt heaters were connected in series across a 230-volt supply, each heater would only receive about 76 volts and produce very little heat. And if one failed, all would stop. That's why domestic and industrial circuits are designed as parallel systems, to keep every load operating at its rated voltage and to improve reliability. Topic J. Differences between alternating and direct current. Next, topic J looks at alternating current and direct current. Direct current, or DC, flows in one direction only, like from a battery or a DC power supply. Alternating current, or AC, changes direction many times each second. In New Zealand, the main supply frequency is 50 Hz, meaning the current reverses direction 50 times per second. In a DC circuit, voltage and current are constant. In an AC circuit, voltage continually rises and falls in a wave pattern. AC is easier to generate and transmit, and its voltage can be changed using transformers, which is why it's used for our national power system. DC is mainly used in electronics, batteries, and control circuits where a steady current is required. So in summary, AC alternates back and forth at 50 Hz, and DC flows steadily in one direction. Topic K. Transposing the formula for impedance. Finally, let's finish with topic K, which links our circuit study to the concept of impedance. Impedance is the total opposition to current flow in an AC circuit. It includes both resistance and reactance, and we use the same type of formula as Ohm's law. We say it like this: Z equals V divided by I. If we want to find current, we say I equals V divided by Z. If we want to find voltage, we say V equals I times Z. Here's a quick example. If an AC appliance has an impedance of 46 ohms and is supplied with 230 volts, The current equals 230 divided by 46, which is 5 amperes. We can speak that as current equals voltage divided by impedance. This shows how voltage, current, and impedance relate to one another in alternating current circuits, exactly as voltage, current, and resistance do in direct current circuits. Summary. To finish, let's summarize what we've learned in Topic 8.2, Electrical Circuits. We began with series circuits, learning that current stays the same but voltage divides and total resistance increases. We practiced how to draw and label those circuits using standard electrical symbols. We then studied parallel circuits, where voltage stays the same and current divides between branches. We learned how to connect measuring instruments correctly. Why all modern appliances are connected in parallel. And how alternating current differs from direct current. Finally, we introduced impedance and simple calculations using the formula Z equals V divided by I. Understanding these circuit principles is a key foundation for electrical testing, troubleshooting, and safe work as an electrical service technician. You'll see these ideas again when we discuss power, energy, protection, and motor circuits later in the course. That concludes Topic 8.2, Electrical Circuits. In our next session, we'll move on to Topic 8.3, Power and Energy, where we'll learn how to calculate and understand the power used in electrical equipment.